Hello, my name is Michelle Stropke, and I am the Riparian and Wetland AIM Implementation Coordinator with the Bureau of Land Management National Operations Center. The following presentation will cover methods for collecting data on hydrology and surface water characteristics within the riparian and wetland monitoring plots. You can follow along in Section 5.3 of the Field Protocol for lentic riparian and wetland systems. Hydrology refers to the movement of water both on and below the Earth's surface, and this movement of water controls the timing and extent of inundation or soil saturation. Hydrology is the driving factor that creates and maintains riparian and wetland areas. Landscape position, climate, topography, surrounding land use, and soil permeability all influence the hydrology of these areas. Hydrology is the defining feature of riparian and wetland ecosystems. The hydrology of a riparian or wetland area is largely responsible for its vegetation composition. Wetlands are flooded or saturated for at least 15 consecutive days during the growing season and often much longer. Riparian areas can be drier but are still connected to and influenced by surface water bodies. The hydrology of a site influences plant communities and favors those species that are adapted to the specific patterns of flooding or saturation found at that site. Hydrology also influences biologic activity in the soil. Soil saturation leads to anaerobic conditions in which soil microbes must adapt to the absence of oxygen. Over time, this can lead to the formation of hydric soil indicators. In this figure, you can see the general direction of water flow into and out of wetland systems. Inputs include groundwater inflow, surface water inflow, and precipitation. Outflows include groundwater outflow, surface water outflow, and evapotranspiration. The position of a wetland on the landscape, the local climate, and the soil permeability of a given area all impact the movement and collection of water on the landscape. For instance, wetlands rarely form in an area with high slope and high soil permeability because water would not accumulate. It would simply flow through. In this basic example, you can see that the yellow arrow is pointing to an area where landscape position and soil permeability are not favorable for wetland formation to take place. The steep slope of the talus field combined with the high permeability of the substrate do not allow for sufficient water retention. The area in the foreground, however, indicated by the blue arrow, is much more conducive for wetland formation to take place. Its position on the landscape allows groundwater and surface inputs from the upland to collect, and its gentle slope is more capable of retaining those hydrologic inputs. Though hydrology is a critical characteristic of a riparian or wetland area, it can be difficult to measure in the field because hydrology is dynamic and variable. The Riparian and Wetland AIM protocol considers hydrology a covariate method, meaning that it is used to help characterize the site for purposes of classification, stratification, or understanding a wetland's ecological potential. Hydrology information is collected in all riparian and wetland AIM monitoring plots. Data collected include evidence of surface or groundwater, dominant and supplemental water sources, characteristics of surface water if present, characteristics of the dominant channel if present, and general hydrology description. The first step is to look for water on the plot. Look for evidence of current surface or groundwater, such as pools or channels of water, or a high water table in the soil pit. Even if surface or groundwater are not observed, look for evidence of past inundation or saturation, such as aquatic invertebrates, drift deposits, drainage patterns, and soil cracks. Refer to the appendix in the protocol for a list of hydrology indicators developed by the U.S. Army Corps of Engineers. Be sure to record the observations using terminology consistent with the indicators where possible. At every riparian and wetland AIM monitoring plot, you will determine a dominant water source and record any additional sources. When determining the water sources influencing the site's hydrology, refer to topographic maps, historic imagery, and wetland classification information. Note that there is an appendix in the protocol that can help you decide if the wetland ecosystem is groundwater dependent. Generally speaking, water sources can be categorized into groundwater, surface water body, and precipitation sources. We will now discuss and define each major water source that could influence site hydrology. The first two water sources all fall under the groundwater category. They include groundwater in general and springs. Groundwater influences many wetlands. Use this water source for repairing a wetland area supported by groundwater that discharges diffusely to the surface or maintains saturated soil within the root zone. Groundwater is often the dominant water source at the base of slopes or alluvial fans where aquifers intersect or approach the land surface. Soils that freeze for extended periods, like permafrost, and subsurface geologic features such as low permeability bedrock or glacial till can cause high water tables, diffuse surface discharge, or subsurface through flow. A spring is a localized point of groundwater discharge. Use this water source to indicate a specific point source of groundwater discharge, such as a spring head. This water source can occur in isolation or in addition to more diffuse groundwater discharge. It may be tempting to record spring as the dominant water source on sample plots named after adjacent springs, such as Coyote Spring or Willow Spring, but use the information you have gathered while sampling the monitoring plot to help inform the most appropriate water source. The second set of water sources all fall under the surface water category. Sites dominated or influenced by these sources are adjacent to and receive water from a surface water body such as a river or stream, pond, lake, or reservoir, or the ocean. The site may be connected to the water body through obvious surface connections, like channelized input or flooding, or through less obvious subsurface connections. For instance, streams or lakes may lose water to the adjacent soil, causing a high water table. Consider the site's landscape position and proximity to a water body, as well as evidence of water flow like drift deposits, flood debris, sediment deposits, channelized flow paths, and plant species indicative of stream processes like cottonwoods. Streams and rivers are common throughout the West. Use this water source for repairing wetland areas on floodplains adjacent to streams or rivers when it is evident that the site receives water directly from the water body via subsurface or surface flow paths. In a typical floodplain, water passes through these sites in the downstream direction via either surface or subsurface connections. However, this water source also covers depressional wetlands found at the terminus of streams. In all sites, flooding and subsurface flow recharge soil moisture in unconsolidated alluvial sediments adjacent to the channel, and water occasionally ponds on the soil surface. Most beaver complexes and associated ponds would be dominant by this water source. Note that in some stream valleys, groundwater may discharge from surrounding slopes along valley margins. If this occurs, consider whether groundwater or the stream is the dominant water source. Adjacency to a stream or river alone is not sufficient to select this water source. Rather, groundwater may be the dominant water source for a site in a floodplain if the site primarily receives groundwater from the surrounding landscape rather than the stream. Ponds, lakes, or reservoirs can be the dominant water source for riparian or wetland areas located on their margins, if the soil moisture regime is tied to rising and falling water levels via surface or subsurface connections. However, like streams and rivers, not all wetlands adjacent to ponds, lakes, or reservoirs are solely tied to the open water body. Consider other sources like upslope groundwater discharge or adjacent streams and rivers. Estuarine, or tidal influence riparian or wetland areas, are located along the coast where the hydrology is connected to and influenced by ocean water. Water levels may rise and fall with daily tidal fluctuations. Surface water in the riparian or wetland area may be as saline as ocean water or may be a mix of freshwater and ocean water. Freshwater inputs are often at deltas, where streams join the ocean and wetlands form at the interface between the delta and the ocean. The third set of water sources are related to precipitation. They include direct precipitation, overland flow, and snowmelt. Wetlands dominated by direct precipitation are restricted to areas where rain, snow, or other forms of precipitation fall to the ground in sufficient quantities to maintain soil saturation. Wetlands dominated by direct precipitation are restricted to areas with high seasonal or annual precipitation, such as northern latitudes. To assign this as a water source, consider whether direct precipitation is the wetland's predominant water source, not whether the wetland occasionally receives precipitation. Wetlands driven by precipitation are rare in the arid West, but common in Alaska. Wetlands fed by overland flow are influenced by diffuse, non-channelized, downslope movement of water over land that occurs when precipitation exceeds the capacity of the ground surface to infiltrate water. Overland flow is considered a water source when the wetland is fed by accumulated runoff from precipitation events, meaning precipitation is an indirect source rather than direct source. Examples of overland flow dominated wetlands include non-channelized depressions like playas or vernal pools that accumulate runoff after large rainfall events and often have low permeability soil or bedrock layers that collect and perch water from immediately adjacent areas. Wetlands fed by melting snowfields or glaciers are found in the upper montane to alpine zones where slowly melting glaciers, snowfields, or snowbanks provide a consistent water source in the spring and summer. Expect to only find these types of wetlands in higher elevation areas that receive significant snowfall. These sites receive water from immediately adjacent melting snowfields or glaciers, not from distant melting features higher up in the watershed. Some types of wetlands are fed by other water sources that do not fall under the groundwater, surface water, or precipitation categories. Wetlands are sometimes formed and maintained by excess irrigation water applied to farmlands. The excess water flows downslope and accumulates into drainages or other low points. Irrigation canals can also seep on the downslope side. In this example, you can see where excess irrigation water has collected in the drainages flowing away from the adjacent agricultural fields. When thinking about water sources, it can be helpful to consider the physical setting of the wetland at the watershed scale. The position of a wetland on the landscape influences the source and movement of water within a wetland. For example, a wetland at the base of a mountain may receive groundwater discharge from the surrounding slopes and/or seasonal spring snowmelt. A riparian area in a valley bottom may be dominated by water connected to a stream or river. In addition to landscape position, taking ecoregion into account can help to understand what hydrologic processes are typical of the greater area. For example, in the arid and semi-arid basins of Nevada, you can expect to find depressional wetlands fed by overland flow or wetlands on slopes fed by springs, while in the alluvial valley bottoms of the Colorado Plateau, you can expect to find wetlands connected to rivers and streams. Surrounding land use, especially groundwater extraction, can influence the seasonality of a wetland. Irrigation practices, including stream diversion and groundwater pumping, can cause changes to wetland hydroperiod. Wetlands adjacent to groundwater extraction activities may experience reduced water levels during the summer and increased water levels in the fall or winter. Be sure to review climate data and be familiar with the recent weather, particularly if there has been a recent precipitation event. In addition, it is helpful to think about long-term climate trends by checking the drought monitor to see if the area where you work is experiencing drought. If so, wetlands in the area may be drier than normal. Once water sources are determined, record if surface water is present within the monitoring plot. If surface water is observed, estimate the extent within the plot, the predominant depth across the entire monitoring plot, and the distribution of surface water, meaning whether the water is concentrated in one water body like a channel or pond occurs in many small patches, or as shallow standing water. Observe and record several characteristics of the surface water, including characteristics of the water surface, such as oily sheens or algal blooms, the smell of the water, and the substrate below the surface water body. Further guidance on these characteristics can be found in Section 5.3 of the Riparian Wetland AIM Protocol. If a channel flows through the monitoring plot, you will need to record its characteristics. If there are multiple channels within the plot, take measurements on the widest, dominant channel. Measurements include channel length, including meanders, average channel width, average channel depth, and the depth of water within the channel. All width and depth measurements will be recorded in bins. In addition, describe the channel or multiple channels if more than one occurs in the plot. In the comments, note whether the channel dimensions were clear and well defined. If variable, width and depth measurements should be taken at up to 5 locations and averaged. Channel length measurements can be checked in GIS in the office with aerial imagery. As the figure shows, channel width and depth measurements of the channel itself are independent of any water present in the channel. Rather, measure the width between the top of the right bank and the top of the left bank. If the top of the two banks are different elevations, measure width from the top of the lower bank to the point where a level line intersects the opposite bank. Depth measurements should be made to the deepest part of the channel. The water level may be above or below the top of the channel bank at the time of sampling. This slide shows the Survey 123 form for collecting channel data. After recording the data in the iPad, take a minimum of 2 photos of all dominant channels observed within the plot during the site visit. Additional details about the number and characteristics of small channels within the plot should be included in the general hydrology description. Here are some examples of channels found in wetland and riparian areas. Pictured on the top left is an example of a small rivulet. On the right is an example of a stable stream. At the bottom left is a site that may not have well-defined channel formation. Measurements in this case might be estimated in the lack of clear edges noted in comments. At each site, you will need to take notes on the general hydrology of the sample plot. Make objective observations and take notes on anything that may impact the hydrology of the site. Include any overall notes on the site hydrology, including inflows, outflows, seasonality, surface water patterns, wetland hydrology indicators, channels, and any hydrologic disturbances. Finally, take overview photos illustrating the extent and distribution of surface water, as well as photos of the features noted in the description of the hydrology of the site, including head cuts, rills, channels, berms, deeply dug pits, or sediment deposition. Record photo numbers and a short written explanation on the photo log datasheet. The photos pictured here represent various hydrologic features of interest. Starting from the top left and moving right, a head cut and resulting plunge pool along a small montane spring, a canal, a spring snail, which is a species of interest in many field offices, evidence of recent beaver activity, and on the bottom row, an excavator and recent dredge pile, and a head cut erosional feature in an area of diffuse groundwater. This concludes the hydrology overview and methods following the Riparian Wetland AIM Protocol. For additional guidance on the hydrology methods, please refer to Section 5.3 of the protocol. Thank you.